Hello, how's it going? In this video, we are going to get our first shader. We're going to hard code everything, but it will be our first shader. This will roughly break down into 3 independent tasks. Task 1 is to write the shader. Task 2 is to write the code which will read that shader, basically, and compile it and everything. And then task 3 will be to integrate everything together and get our thing working. By the end of this video, we should have a triangle on the screen. Exciting, I know. So, task 1, writing the shader. What I'm going to do is I'm going to go to my source folder and I'll make another folder, shaders. And then I'll make a file inside there called shader.wgsl. Now you'll see that VS Code has recognized this file extension, and that's because I've got an extension installed. If I go over to extensions and I search WGSL, just in life, if you search your file extension, generally there's something for it, and there's a syntax highlight for WGSL, and that's what I'm using. But anyway, so roughly speaking, the shader is going to split into, well, there are 2 programmable stages where I'm going to interject. One is at the vertex stage. So I'm going to make a function. It does some stuff. I'm just going to leave that for now. And then we'll also have the fragment shader function. Okay, so the task is to draw a triangle, and the way this works is, imagine you've got your triangle and you're going corner by corner. The vertex shader is going to be invoked for each of the corners, and as a matter of fact, it can be invoked in parallel. And then its job is to write data which can be interpolated to a per pixel level, and that's what the fragment shader is going to pick up on. So the fragment shader will be invoked for every single pixel inside that triangle. But I'm going to need some sort of communication protocol between these, and it turns out that communication protocol is the return value of the vertex shader. So we can actually specify which sort of data we want to put out from our vertex shader, and that will be the same, well, the input there will come into the fragment shader. So before I worry about the shaders, I'm going to declare a struct, and it's not too exciting. Okay, so yeah, I'm just gonna change this a little bit. Also gonna have color, and that will be govec3, something like that. So we've got 2 attributes that we're writing to. We're writing position and color. And position has a special meaning because when we write to this variable, that will be the position on the screen where that point appears. Whereas color is more of a custom attribute, or of a custom variable. But yeah, so the shape of this code is that our vertex shader will put out one of these vertex payloads, and then our fragment shader for its input stage, we'll have the vertex payload, but there's a few more things I need to include. So the output of the fragment shader, its goal will be to write to the screen. And so it will write out to location 0. Location 0 will be the color attachment that we're writing to. There we go. I think that's fine. So we just take the RGB color, put on an alpha value of 1, and that's it. We've got that there. Now, in terms of the vertex shader. So for the vertex shader, going to code in a bunch of positions and colors. Like I said, it's going to be hard coded. I'm not going to worry about shipping data to the GPU just yet, just hard code it. So the convention here with screen coordinates is basically that negative x is to the left of the screen, positive x is to the right, positive y is at the top of the screen. Let's find out, actually. Maybe I got that wrong. I don't know. Let's see. It might be a little different on WGPU. But anyway, we've got our positions hard-coded. I'm also going to get... There really will be nothing too new here. This will just be the standard RGB triangle. Cool, there we have it. So we have a set of positions, we have a set of colors. What I want to do for the given invocation of the vertex shader is select which of those we want to use for our triangle corner. And in order to do that, I need to know which corner we're drawing. So the way I'm going to do that is I'm going to use an inbuilt variable, which is basically the vertex index. So I'll put this qualifier here, built in. Okay, then we have it. So now we're ready to go. So I have our output variable. So I'll talk a little bit more about this trailing one when we get into matrix transformations, but long story short, it is necessary. This 0 here we're putting for Z, for the depth, and this is putting this object at the screen level, if that makes sense. And we're also going to need to set the color. Cool, okay. So again, the invocation of the shader will just be binding no data and just telling it to dry run like a number of times. That will have the effect of setting this vertex index I, which we're taking in as input. And based on that, we populate the appropriate data into this structure, return that structure, and then that is passed along to the fragment shader. So that is, fingers crossed, that is the shader done. Okay, so the next task is to write the code which will load the shader. So I'm just going to go back to my source folder, make a new folder. I'll call this, renderer backend. And I'm going to need two things in here. One thing is I'm going to need the source file that I'll write. I'll call this pipeline builder. Okay, and then I'm going to need to describe this. So I'll have module file mod.rs. So the purpose of this module file is to declare all of the source files in the module. So I'll say public module pipeline builder. Great. And then I can go, actually I'll leave that for now. Okay, so I'm going to sort of spiral into this one bit at a time. To start with, I'm going to need a struct, which is my pipeline builder. And that's going to have a few things. We're going to have, going to store the names of the shader modules that we're going to, well, first up the file name and then the names of the entry points within that file. And then I'm also going to be storing the pixel format. Right, so currently this isn't really seeing WGPU because it doesn't know that this module is being used in my project which uses WGPU. So what I can do is I can go to my main and then I can just say mod, not use. There we go. And then if we go over to the pipeline builder, we can now see that that is all being recognized. Excellent. Cool. So on with the show. Let's look at the methods for this struct. There we go. All I'm doing is creating one of these things, populating them with sensible, or in some cases unsensible, default values, and returning it. Great, so we've got that, but I'm going to need two more modifier methods, and their purpose will be basically to populate the file names and entry points, and to populate the pixel format. There we go, just a simple setter. I'm taking copy constructors of the given input, but yeah, otherwise it's pretty straightforward. Great. Okay, so the usage of this thing, intended usage, is we create one of these things, we use these setters, and then we tell it to build. And along the way, if we want to build multiple pipelines, we can just selectively reset what we want to. But now for the big one. Just going to make a few modifications here. In order to do this, I'm going to need a few things. It's going to need to resolve some file paths. So I'm going to use the current directory, and file stream will be useful as well for loading stuff. We've got it. So this is doing the basic job of looking in that file path, reading the physical contents, and dumping that out into a string. Perhaps just a little note here that we start with this file path as a path buffer, and we're setting it up, but then we sort of coalesce it into a different data type. And this is totally fine. It's covering syntactic sugar of like file path 2 equals file path. Totally fine because of Rust's borrow checker and restrictions. We have the guarantee that this is the only usage up to this point of file path as a path buffer, and there's going to be no reusage at a later point. If we did, we would get errors. But yeah, so again, we've read the file. The next thing I'll need to do is describe the shader module. And the interesting thing about this is that because I've got this all in one file, I can actually have this all as one module. And then the fragment and vertex stages will pull from that single module. But anyway. Now, the next part will be to describe the pipeline layout. Now, the idea of a pipeline layout is like the shape, the basic shape of which resources will be bound when we run this thing. There are two things. There are bind groups and push constants. Now, a push constant is a quick way to get data into a render pass. That data is live when it's pushed. That's it. It exists, at that point. You can push multiple different parts of data at different stages, just the same way that you would with uniforms, except that push constants are a little more limited in the size of what they can accept. And then we have bind groups, and those are large long-term resources which persist for the lifetime of the draw call, basically. So if you change a binding, that changes everything. Usually they're just bound once up front for the whole draw call. As you can see, we really are not binding any resources, so it's pretty straightforward at the moment. At a future point, we may abstract this out into another method if we want to change the bindings for different pipelines. But anyway, the next stage is I'm going to need to describe the render targets. And the render targets are basically what we want this thing to write to. In this case, we want it to write to color. The color attachment. Okay, so final stretch now. I'm going to basically describe my render pipeline, and this involves populating all of the stages, more or less. Okay, so we populate our vertex stage. Now just a quick note that we've got this bind group, and in this bind group we can bind a whole bunch of buffers, and then similarly we can bind buffers for the vertex stage. Now the difference here is that these are vertex buffers versus general like storage buffers. There we go. Now here we're describing the parameters for the input or primitive assembly stage. So the way this goes is we hit it with the vertex shader first. That transforms all the corners of the triangle, and then that together is put with the primitive assembly. That puts it into shapes, and that goes to the rasterizer, which interpolates everything. And the rasterizer gets things down to a per pixel basis and then dispatches them to the fragment shader, which is what we'll now describe. Okay, I guess the only thing which I think is really interesting is that the fragment shader is explicitly an optional stage. This could be useful in some things like early depth testing, although I have heard that in practice early depth testing is not as popular these days because the performance benefits just don't seem to be there as much as they used to. I wouldn't know, but anyway. So there we have that, and then I just need to specify a bunch of other little final stages. And that should be it. Now just a note that for whatever reason on my MacBook, originally this was working with a mask of 0, but it wasn't working on Linux or other systems. A subscriber helpfully commented that we could flag this to all ones by just going not 0. And I also found that if I just put in 1, that also works. So your mileage may vary. Be aware that this may have to be tweaked. I think I'll just in case, because it's going to work on my system no matter what, because my system's weird, but we'll just keep that. Okay, so that's the describing done. Now we finally need to return this thing. It just wasn't linting it properly, I guess. Okay, great. So that stage is done. We've got our pipeline builder. Its job is to build a pipeline. That's what it will do. Now the final stage, which is to bring everything together. So I've now specified that I'm going to need a render pipeline in my state as well. So I'll go right down, I guess down here. Okay, excellent. So we have this pipeline builder, we set the state and then tell it to build. That gives us a render pipeline, which we can then put in. It's gonna have to do the Rust dance, as they say. Okay, cool. So we've gone ahead and built the pipeline. Now we can get down to the rendering bit. Okay, so we've got this begin render pass thing, and that actually returns a render pass object. So what we can do is we can say begin the render pass, get that render pass, and start working with it. So we'll take that render pass, so that shade is now good to go, and then I'll tell that render pass to draw. Vertices, I'll go vertex 0 to 3, and then instances, I'm not using instanced rendering, so I'll just have one instance, the default. Cool. Now, we are going to have an issue here, and the issue is that, okay, the issue is that on this line where we made this render pass, we sort of borrowed the command encoder, and we've got this render pass object which is possibly modifying the command encoder, and Rust is as conservative as possible, so there is the possibility that there was another thread or something. There's the possibility that somehow this render pass is going to get modified, especially since this is going on the queue. But anyway, long story short, we can scope this and say, yeah, this render pass is going to be sort of tied up with the command encoder. It's going to be possibly modifying the command encoder, but that's only for this explicit scope. And then Rust says, okay, I got you, no worries. Cool, so let's get down. So I missed this because I improvised it on the spot, but basically if I have a variable that I'm just arbitrarily passing through, even if it's not bound to a specific vertex buffer, it does need to have a location, I guess, a binding. Let's see how this goes now. Oh yeah, nice. And 100% I did get that wrong. So let me just debug that triangle. Okay. So we have, yeah, that's right. These two are bottom left, bottom right, and then top center. Fingers crossed. There we go. Perfect. Excellent. Okay, so that's been fun, I hope. In the next video, I'm going to have a look at not hard coding the data, but actually passing the data through from the computer to the GPU. And I hope to see you there, but that'll be it for now. All the best. Bye.